You guys are going to get a brief introduction to organic chemistry today, as far as understanding what organic chemicals are, recognizing their formulas, and then simple naming. That's the scope of today's discussion. Okay. Organic chemistry, there's probably somewhere in the order of about 5, maybe 10 million molecules out there that we know of. Okay, that's a lot, but there's many ways we can put atoms together. I mean, we basically have 118 atoms. It's basically the alphabet of matter as we know it, and we can put these things in any proportions that we want as long as they're stable. But it's pretty surprising that one particular atom, the carbon atom, accounts for about 95% of the chemicals that we know, and then the other 117 elements represent about a small portion of that. That's inorganic chemistry. Of the 5 to 10 million molecules that we know, about 500,000 are inorganic. The rest is organic compounds. Okay? Why is organic? Why does it encompass so many chemicals? It has to do with the stability of the carbon atom. Organic chemistry is the study of carbon-containing compounds. Okay, it's the study of carbon-containing compounds. If it doesn't have carbon in it, it's not organic. If it has carbon in it, then we consider it an organic chemical. And that was pretty amazing because we thought for the longest time that the organic chemicals can only be found in living tissues, living things, and we could only isolate it from living items, living beings, okay? And we find out later that we can actually synthesize organic chemicals in the lab. A guy by the name of Friedrich Euler was the first scientist given credit of synthesizing an organic chemical. Back then, right around 1828, they thought, like I said, you can only find organic chemicals in plants or animals, and you can isolate it by extracting it. He took ammonium chloride, silver, nitrogen carbonyl, and he synthesized this chemical right here. This chemical is called urea, and urea is the active ingredient in urine. Okay, so just based on that synthesis, he was able to synthesize a chemical that a lot of us produce. Okay, and that started organic chemistry. People realized that these things can't be made in the lab, and they started to make a lot of organic chemicals. You can make all of these in the lab. Okay, ethanol, you can do that. You can synthesize that. Caffeine, my favorite drug. Okay, we can do that. We can make artificial caffeine. Other chemicals are not so good for you unless you are taking it for medical purposes. That's the key. Okay, THC, tetracyanocannabinol. That's the active ingredient in grass, pot. Okay.
I haven't heard grass in a long time.
Well, I come from the 80s. Okay, we used to call it pot or reefer, things like that. Mescaline, that's the active ingredient in Picoti cactus, and people extract that. So there's LSD was synthesized in the lab, and a very, very small amount will get you very, very high. I mean, John Lennon, he wrote Lucy in the Sky with Diamonds. I mean, LSD is Lucy in the Sky with Diamonds, based on the high that he got. And if you listen to the lyrics, it's exactly the high that people get when they get, don't take it, but they see kaleidoscope colors. And it's because these organic chemicals interact with your neurons in your brain, and it gives you a different perception of reality. Okay? That's why organic chemistry is so important, because it can cure health problems, but it also can make things worse if you don't know what you're doing. Okay? A couple of things that I want to review for you is the number of electrons these atoms have. The reason why we concentrate on these atoms is because these are the atoms in 90% of organic compounds. Okay? Carbon, definitely 100% in organic compounds. They have 4 electrons. because they have 4 electrons in their valence shell, they can do 4 bonds. In fact, carbon always has 4 bonds. Okay? The exception is carbon monoxide and carbon disulfide, but carbon always has 4 bonds. If you are planning to go on to graduate school and go into, medical school, and you're taking organic chemistry, if you forget that carbon has 4 bonds, you're never going to make organic chemistry. Okay, that's a cardinal rule in organic chemistry. Carbon has 4 bonds. Hydrogen with 1 valence electron prefers 1 bond. These are the example. Nitrogen, 5 valence electrons, 3 are unpaired. That means it can do 3 bonds, but sometimes it can do 4. Okay, nitrogen can do 3, sometimes 4. Oxygen with 6 valence electrons, 2 are unpaired, so it can do 2 bonds. 2 bonds, mostly, it can also do 3. Okay? And then the halogens, because they have 7, 1 is unpaired, they prefer 1 bond. The halogens and the hydrogens tend to have 1 bond. And then just remember these, because when you write organic formulas or organic structure, these are the rules you need to go by. Carbon always has 4, nitrogen 3 or 4, oxygens 2 or 3. Okay? That's just a review of molecular geometry that we covered back in chapter 4. Now, these are chemicals. Methane is this compound right here. You can see that it's got a carbon in the center and it's got 4 bonds, and all the bonds are single. Okay? The neat thing about organic chemistry is there is an organization to their madness. Okay? And that organization is that the name, the prefix in the name generally tells you how many carbons there are in the compound. Okay? Meth means 1 carbon. Eth means 2 carbons. Pro means 3. We'll talk about that later. And then the A and E ending tells you the class of organic compounds it falls under. The A tells you there's only single bonds in this compound. So, like I said, there is an organization, there is a logic to the madness of organic chemistry. You have to know the rules. This is methane. This guy right here is ethene. Okay? F, remember I said, was 2 carbons? 2 carbons. The ene ending tells you there's a double bond. Okay? If it was ethane, it would be this, where there was only single bonds throughout. Okay? And that F meaning 2 carbons, A meaning single bonds throughout. But we have ethene here, so it means F meaning 2 carbons, E meaning there's a double bond. Okay? We'll talk more about that shortly. Ethyne, F meaning 2 carbons, Y and E telling you there's a triple bond. The bond angle here is 180. The bond angle here is 120. It's trigonoplanar. The bond angle here is 109. It's tetrahedral. Okay? So these are the different class of compounds that we are going to be concentrating on today. The alkanes, called alkanes because they are single bonds. The alkenes, it's a double bond. And alkynes, it's a triple bond. I will show you that slide of these class of compounds. These are the bond angles. You don't have to worry too much about the hybridization. We covered that back in molecular geometry, but we didn't really expand on that. When you get to 130, you will do an in-depth study on that. Let me do this now because this is the important slide in terms of understanding organic chemistry. How do we represent organic compounds? And we represent organic compounds in many ways. One is through their chemical formula or their molecular formula. Their chemical or molecular formula simply tells you the type of atoms and the number of atoms. Okay, the type and the number. The formula that you see here, C2H60, tells you there are 2 carbons. The carbons are black. There are 6 hydrogens. The hydrogens are white. 2, 3, 4, 5, 6. And 1 oxygen. But this is one arrangement of that molecule, or one arrangement of those atoms. This is another arrangement of those atoms. You notice this too has 6 hydrogens. 3, no, this is not right, sorry. I messed up, because this has 3 carbons, and I should have only 2. So it's actually this. Okay. 2 carbons, 6 hydrogens, and 1 oxygen. Likewise with this. 6 hydrogens, 1, 2, 3, 4, 5, 6, 2 carbons, and 1 oxygen. These are different chemicals because the way the atoms are connected are different. We call these isomers. Okay, isomers are a chemical with the same chemical formula but different structural arrangement. Chemicals, compounds with the same formula but different atomic connection or arrangement. So these two are isomers because these guys have the same formula, but they have different atom conductivity. Okay, isomers is very common in organic chemistry. Isomers are very common in life chemicals. Okay, chemicals responsible for life. So if you take 130, you've got to know your isomers. And the key to knowing isomers is to have a good eye for 3 dimensions. Because you're going to have to take a molecule, rotate it in your mind's eye, and see it from a different perspective to compare whether that molecule is the same or different from another chemical. Okay, because sometimes they'll look the same. Take a look at these two right here. Okay, these two are called stereoisomers. And the reason why they're called stereoisomers is because they look the same in 3-dimensional view. I mean, you have red, white, purple, and black. And if you just look at it, you would say, yeah, they're pretty much identical chemicals. The key in figuring out whether they're isomers or the same, okay, same chemical, is to superimpose the atom to each other. Take, for example, your hands. Your hands have 5 fingers. The thumbs and the pinkies are at the end. But they're not the same because you can't put your left hand into a right glove. They are optical isomers. Okay? Because they are a mirror image of each other. And that's what these are. These guys are a mirror image of each other. If you take a look, I can line up the black, the white, and the purple, and the reds are in the back. If I try to superimpose them now, I can line up the red, the purple, and the black, but look what happens to the reds. There is no way I can twist and turn this to get one on top of the other. The only way I can do that is by literally taking apart the atom, moving the bonds, and rearranging it. That means a chemical reaction has to occur. Then and only then can I align all atoms together. You can see the purple, the black, the red, and the white are now lined up. These are identical. But, going back to this, these are not the same atom. These are optical isomers. And when you take organic chemistry, optical isomers can be a real pain in the behind. Okay? So I will pass this around and you guys can take a look at that. So one way of figuring out the identity of a chemical is through their chemical formula and then their structural formula. The structural formula is just the way these things are drawn in a 2-dimensional arrangement. Ethanol looks like this. It's got 1 carbon and 3 hydrogens attached. Remember, carbon always has 4 bonds. this carbon is attached to another carbon, a hydrogen, and then an OH. That's ethanol. Okay? The other isomer is called dimethyl ether. The reason why it's called dimethyl ether is because you see this carbon right here, next to the oxygen? It's only got one carbon, right? The prefix for one is meth. So it's methyl, because it's part of a chemical, and there's two of them. That's why it's called dimethyl. And the oxygen in the center tells you it's a special class of organic chemical called ether. That's why it's called dimethyl ether. And so this compound looks like this. It's got 3 hydrogens on the first carbon, an oxygen, and then that's dimethyl ether. Okay? These are the structural formulas, and you can see that it certainly gives you a perspective of how these things are connected. The problem with structural formulas, especially if you have to make a piece like this, okay, is that it takes forever to write. Okay, it takes forever to write. So, and you guys are going to have to write a lot of pieces like this in organic chemistry. So there's got to be a simpler way to do it. Okay, and I will show you the simple way. The condensed formula came because back in the days, like when I was growing up, we didn't have computers. We had typewriters. Okay? It's a pain now that I think about it. You make a mistake, you have to take out the whole paper, or you do the whiteout thing. It's a pain. But these days we have word processor that you can just delete it from memory and correct it. Okay? But in a typewriter, because you are stuck with one line, they have to figure out a convenient way of writing these things in one line. It'd be very difficult to write this in one line. Okay? So how do they do it? They do it through the condensed formula. The condensed formula is nothing more than a string of characters in one line. You see this chemical, this part of the chain right here? Well, I can represent that by CH3. Okay? Or I could represent that as H3C. It's the same in organic lingo or chemistry lingo. It doesn't matter what order you put it in, you know that carbon has 4 bonds. And then this part right here, that's a CH2. Okay? And then finally the OH is special, you write OH. So you see how I took this and made it one line? Well, that's the condensed form. This guy right here, I would write it this way. I could write it as CH3, O, CH3, or I could do this, H3C, O, CH3. When I do it this way, I'm showing that the hydrogens are connected to the carbon is connected to the oxygen is connected to the carbon that has 3 hydrogens. This way, I know that this carbon always has 4 bonds, remember. That's a very important rule. So this carbon has got to be attached to 3 hydrogens. That accounts for 3 of the 4. The 4th bond has got to be to the oxygen. Okay. Another example would be something like this. And again, you can see that when I draw the structure, it's sort of tedious because then I have to draw all these lines and all these atoms. But if I can draw the condensed form, then I don't have to worry about the lines. The condensed form for this would be CH3, CH2, 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 CH3. Okay, that's the condensed form. Or I can do this. CH3, parentheses, CH2. How many CH2 do I have here? 3. So I put 3 down there. And then CH3. Okay, and I put a line there. Meaning that there are 3 CH2 groups that are connected in a chain, and then the ends are CH3. That's a condensed form. You notice I can do this in a typewriter. If you can do it in a typewriter, it's considered a condensed form. Okay? So that's one way of showing the structure for organic compound. The shorthand notation, you see how these things are nothing more than carbon and hydrogen? These things are also called hydrocarbon. hydrocarbon. In organic chemistry, hydrocarbons are very stable. Reaction do not take place in hydrocarbons because the bonds are strong. They always attack the anomaly or the weird structure in the organic chemical, the OH group or the oxygen group. Okay? The oxygen group in dimethyl ether. They always attack that because those are going to be sites where it's going to be unstable for that chemical. So rather than name, because this is the most important part of the organic chemical, we can make this a shorthand notation by representing it as R. R just means hydrocarbon. No, it means carbon and hydrogen. Okay? And then the important part of this chemical is the OH, so we write ROH. Okay? A hydrocarbon attached to an OH. This type of chemical are called alcohols. And when you see this, you're talking about a class of compounds with OH or alcohol. Another example might be this. You guys have seen these light. Okay? You've seen this guy. This is an alcohol. This is methanol. It's got a carbon here, 3 hydrogens, and an OH. That's methanol. CH3OH. I can represent this as ROH. Or ethanol. Okay, it's got 2 carbons. That's why it's F. Methanol. All tells you it's an alcohol. Okay. I could also represent it as ROH. They're both alcohols. This guy is this. It's got 2 carbons, a double bond oxygen at the end. This guy is called ethanol. Notice the AL ending. If I want to represent this in a shorthand notation, I would write R, carbon double bond OH, because this is the important part of the structure. Okay, these things are called functional groups. Listen to the name, functional groups. Functional meaning that that's the important function of that compound, and it's a group. The last example I want to show you is this chemical right here. This chemical is a chemical that you guys have worked with a lot this semester. Okay? Anyone know what this is? Acetic acid. Okay? It's an organic compound. It's an organic compound. The formal name of this, the common name is acetic acid, but this is also known as ethanoic acid. You see why it has the prefix etha? 2 carbons. Okay? Ethanoic acid. And then the ic acid tells you that this part right here is the important functional group. I can write a shorthand for this by writing R, carbon, double bond, oxygen, OH. Okay?
What are functional groups?
Functional groups is this right here. Let me show you this slide. It's that part of the organic compound that is responsible for the type of chemistry that occurs. So these are all functional groups. The OH in the organic compound, like in methanol and ethanol. That's the functional group. Okay? It's called functional because that's the main chemistry that occurs is based on this group. Okay? Notice the suffix OL. Whenever you hear an OL in an organic name, you know it's an alcohol. Butanol, pentanol, ethanol, glycol, cholesterol, OL. They've got that OH group in the structure somewhere. Okay? Ethers, it's going to have ether in the name. Dimethyl ether. Ethyl methyl ether. Okay? It's got an oxygen embedded in the center. Hydrocarbons are at the end. Aldehydes, the oxygens are at the end, just like what we have here. These are aldehydes. Don't worry too much about memorizing them because this sheet is part of your equation page, okay? Just recognize them. If I give you an organic compound and I ask you to circle all the functional groups, you should be able to do that. And then you're just looking for these, it's like looking for Waldo or something. You just look for these things in the structure, you circle it, and then you name it. Okay, that's the extent that I'm going to ask you in terms of finding these things.
Are they going to be red?
Are they going to? No, they won't. You're going to be highlighting, okay? This one right here is a ketone. A ketone's an oxygen in the center. Okay, it's not at the end. Carbon double bond oxygen in the center. The ending is ONE. That's the suffix. Okay? A carboxylic acid is got this structural motif right here. Okay? It's got ic acid at the end. Formic acid, acetic acid, butanoic acid. Ic acid tells you it's a carboxylic acid. Okay? Esters looks like this. Got a carbon double bond O and then OR. This is OH, so it comes at the end. This is in the middle. Okay? Amines is nothing more than nitrogen with 3 groups attached to it. But it's different from an amide because an amide has the nitrogens and next to it is a carbon double bond oxygen. Notice that carboxylic acid has an OH and an aldehyde. But carboxylic acid is more important than the aldehydes or alcohol, so it has a higher priority. You don't name this when you're looking for functional groups as alcohol and aldehyde. Because they have those characteristics, you name it as a carboxylic acid. Okay? So, take a look at that. Take a look at the sample test because there's a question in there in which I give you a weird structure. I don't ask you to name it. I just ask you to circle the functional groups and indicate what those functional groups are. Okay? So that shouldn't be too difficult, especially if you have this in front of you.
Yeah.
Okay? Yeah, you will have that in front of you. Okay? So, that's the shorthand notation. The stick notation is probably the best notation that you guys should understand and learn today because you will see a bunch of questions on that. Let me erase this. Stick notation is based on writing structures based on lines. Stick notation is a skeleton method of drawing organic compounds. Okay, something like this. Okay, if I had to do the structure with the hydrogens and everything, then it'll take me a while. Through the stick notation, I can probably do it in under 30 seconds. Okay. What exactly is the stick notation? Well, this compound right here, I would represent it this way. Okay? See how easy that is? It requires less work on me, more interpretation on you. Okay? So, that's the difficult part about the stick notation is that initially, it requires greater work from the audience. But once you figure it out, it goes like that. This guy right here, the dimethyl ether, remember, looks like this. Oxygen in the center, CH3 at the end. Looks like this in terms of the stick form. Okay, it looks like that. And let me just sort of elaborate on these so that you guys know exactly where I'm coming from. You see the beginning of lines and the angles of lines are implied that you have carbons. Okay? This is the backbone. So the beginning of lines and the bends of lines are carbons. So I have a carbon here. I have a carbon here. You see how this line ends at an oxygen? I don't have a carbon there. I have this line connecting to an oxygen. So that's what this means. What is the cardinal rule in organic chemistry?
4 bonds per carbon.
Okay, 4 bonds. When you don't see hydrogens in the compound, the hydrogens are implied. That's the other cardinal rule. 4 bonds, hydrogens are implied. So right now you see only 1 bond with carbon, right? It's missing 3 more. You need 3 more. Those are hydrogens. Because hydrogens are implied.
We have to write that.
You don't have to write it, but I'm just showing you how this translates to this. This carbon has 2 bonds, right? How many hydrogens have to be attached?
2.
Exactly. 1, 2. Okay? So that's the magic of the stick form, is that you just draw the backbone. Carbons has 4 bonds, hydrogens are implied. This guy right here, this is a carbon, it's attached to an oxygen, this oxygen is attached to a carbon. Because there's only 1 bond that you see, there has to be 3 more hydrogens. Okay? And these stick forms are so much easier to draw than these guys. Okay? Stick form. Now, let me elaborate a little bit. Let me erase this and let me show you how I would represent this as a stick form. How many carbons in this compound? 5. Okay? So the way you do the stick form is just 1. When you put your pen on the line, that's 1 carbon. 2, 3, 4, 5. That's this. I put a carbon here, carbon here, carbon here, carbon here, and a carbon here. This has 3. This has 2. This has 2. This has 2. This has 3. 3, 2, 2, 2, 3. Now, you might say to yourself, okay, that looks similar. It's up and down. Okay? But I can also draw this way. And the reason why I can do that is because single bonds have free rotation. Okay? They can rotate. So you can just contort it in any way you can. But as long as the carbons are lined up and you have 1, 2, 3, 4, oops. 1, 2, 3, 4, 5 carbons, it's the same compound. I can take that zigzag formation. Okay, I can take that zigzag formation, just like this. Okay? And I can make that by simply twisting these around. And that's the key to organic chemistry, is that you really have to know the difference as to whether these are the same through twisting and turning and not breaking bonds, or isomers, where I have to break bonds and move things around. This too has 5 carbons. This too has 5 carbons, but there is no way I can twist and turn this to make any of these. So these would be isomers. Okay? There's no way I can twist and turn this to make it look like that. On the other hand, because single bonds have free rotation, and that's why if you take 130, it would help a lot. If you did some models, you need to do that. Okay? So that's the stick form. Okay? The stick forms are the best way to represent organic compounds. I already talked to you about isomers. Okay? So let's take a look at, I talked to you about functional group. These are the class of organic compounds that are generally out there. This is the family tree. You have something called hydrocarbons. Hydrocarbons are nothing more than chemicals in which you have carbons and hydrogens. Carbons and hydrogens, that's all you have. Okay? And then you have heteroatoms. You throw in an oxygen, you throw in a nitrogen, you throw in a sulfur, okay? You throw in a halogen, there are heteroatoms. In terms of the hydrocarbons, you've got alkanes. Alk in the prefix, alk or al means hydrocarbons. Notice al, 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 al. Al means hydrocarbons. You've got carbon and hydrogens. Ane tells you single bonds throughout the chemical. Ene tells you somewhere in there's a double bond. I tells you somewhere in there's a triple bond. And cyclo tells you somehow they're arranged to form a cycle. Okay, a cycle. That's when you take one end and you attach it to the other end. You can do that by removing a couple of hydrogens, and making it connect that way. So that would be, how many carbons in this compound? So this would be a what? It would be pentane, but the fact that it's in a circle tells you it's a cyclopentane. Cyclopentane. Pent meaning 5, ane tells you there's only single bonds throughout. So see, there is a organization to all of that. The key to organic chemistry is you have to memorize all those rules. Okay? You need to memorize all those rules because they've got a lot of rules. That's why I do like it. That's why I'm not an organic chemist. I like to see what I'm doing rather than pulling it out of my head. Okay? Alkanes, also want to tell you about the general formula. Alkanes are CnH2n. If you know the number of nitrogen, if you know the number of carbons, you can calculate the number of hydrogens. Alkenes are CnH2n. This is 2n plus 2, this is 2n, and this 2n minus 2. And that's because as we go from single bond to double bond to triple bond, and that's shown right here, as we go from single bonds to a double bond, if this were single bonds, for example, like right here, we have to remove 2 hydrogens in order to get that second bond to work. Okay, 2 hydrogens have to be sacrificed to get the second bond to work. So that's why, compared to an alkane, this has less 2 hydrogens. Compared to an alkene, this has less 2 hydrogens. Because you are always removing a couple of hydrogens when you make a bond, because you need to use those electrons. Okay, so like I said, if you take a look at alkenes and alkynes, you can see that these two have different. This thing has 4, this thing has 2 carbons. Let's go back here. How many carbons in this structure? 5. How many hydrogens do you think there are based on this formula? Oh, exactly. And if you want to verify it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you know it's an alkane, you don't even have to count. You just use that formula. If you can count the number of carbons, you can also predict the number of hydrogens. Okay? If I gave you a compound that looks like this, okay, I gave you a compound that looks like this, and I can be very creative. Okay? How many carbons?
12.
A lot more.
I said 13. I said 7. I said 13.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
I was 1 off.
Okay? So you guys need to be able to find the carbons. Okay? It's generally in angles. So we know there's 12. How many hydrogens?
26.
Exactly. And I can do that, I can count, but I'm not going to bother. Okay? There are 26. If there is a double bond in here somewhere, it's still C12, but now how many hydrogens? 24. I've just sacrifices the hydrogen from here and here to make that double bond. So it's always less 2 hydrogens, yes.
Can you explain the hydrogen thing?
The hydrogens, how I predicted that?
I did like 2 now.
The formula is this. If you know the number of carbons, you can predict the number of hydrogens by this formula. Because we found out that there was 5 carbons, 2n is 10, plus 2 is 12.
Oh,
Okay, so we just use the formula. Because we know there's only single bonds throughout. Oh yeah?
Every double bond, you're going to lose 200. So you're going to have.
What was that? Because these guys only have single bonds. Do you see in the previous example, do you see a multiple bond in there? It's only single bonds. So we're using that. If you see a double bond in the structure, like right here, if I have that, and you see a double bond, then I will be an alkene. Okay? So just by looking at the stick notation, you know whether it's an alkene or alkyne. Okay? So now that you understand that, let me this is also on the online, so you can take a look at that. Remember I told you that the prefix tells you the number of carbons? Well, these are the alkanes. Alkanes for meth 1, F2, 10, coke, 3, bute 4, pen 5, and then we go all the way to 10. You have those prefixes as in your information page. Okay? If you look at the back of your lab manual, there's a chart there for organic chemistry. That's basically what you will find. So these are the different alkanes. And how do we know they're alkanes? There's only single bonds throughout these compounds. Single bonds tells you they're alkanes. They follow this formula, CnH2n+. Okay. Alkyne, there's a triple bond in there. Alkyne, if you look at the structure, somewhere in there, there's going to be a triple bond. And the way you draw triple bonds, because these things have to be linear, you see it this way. It's the same, it's not an angle. It's just a break, and then you go to the triple bond. So this is one carbon because this is an N, this is another carbon, and then these are other carbons. So when you see 3 lines, the beginning and the ending of those 3 lines are carbons. And it has to be drawn in a linear fashion.
So when you see that, then you have to use that.
Minus 2, exactly. Okay. So take a look at these because you notice that pentane, there are many ways of rearranging 5 carbons, and these are isomers. Take for example this. I don't have the hydrogens shown. It's very simplistic. Pentane. 1, 2, 3, 4, 5. One is all the carbons attached side by side. But if I take one of the carbons at the end and attach it to the middle, right here, you can see that it's still got 5. This also is a pentane. Okay? So this would be an isomer. If I take one of the carbons and put it into right here, that also has 5 carbons, and that would be an isomer. The fact that it's only got single bonds and 5 carbons tells you it's a pentane, but these are different isomers of pentane. Okay, and the way you determine isomers is through trial and error. Why do you think that there's so many organic compounds? Because when the chain gets longer, there's more ways to arrange them. So I think with 6 carbons, pentane has 3, 6 carbons have 7, 7 carbons has about 11, 8 carbons has about maybe 20, 22, and then it just takes off exponentially. If I was really mean, I'd ask you to draw all the isomers of non-A. That'll take you the whole period. Okay? It'd be very difficult. So I won't be mean. Okay. Real quickly, you can see that this structure right here has 1, 2, 3, 4, 5, 6, 7, 8. It's an octane. It's a specific isomer of octane because it's got 8. But I want to illustrate a couple of things. You see these carbons at the end? They're only attached to one other carbon. These are called primary carbons. Primary because they are only attached bonds to one other carbon. Okay? This carbon right here is attached to 2 carbons. Here and here. It's called a secondary carbon. This carbon right here is attached to 3. It's called a tertiary carbon. And this carbon right here is attached to 4. So it's called a quaternary carbon. If you can count the number of primary, secondary, tertiary, and quaternary carbon for isomers, they will be different. So that's another way to verify whether or not they are the same or they are different. Because the number of primary, secondary, tertiary, and quaternary carbons for isomers will be different. Whereas if they were the same compound, they would have the same number. So the degree for the carbon has to do with how many carbons they are attached to. Okay? Let me move on. This is an important chart because it tells you the prefix also went to 10. Okay? Dec is 10, non is 9, oct is 8, Hep is 7, hex is 6. Okay? Many isomers. Now, this is the last part I'm going to talk to you guys about. This is the naming portion. And when you name these things, okay, you have to understand the rules of naming. So I will go through these real quickly and then I'll end there. You notice pentane has 3 isomers. Hexane has 1, 2, 3, 4, 5 isomers. Actually, it's got 5 isomers. These are it. And you notice that the names are different for each. Even though they're hexane. And why are they hexanes? Because they've got 6 carbons and single bonds. But because they are isomers, they have unique name based on the rules we give it. It's called the IUPAC. IUPAC stands for the International Union of Pure and Applied Chemistry. So it's called the IUPAC nomenclature. IUPAC nomenclature. And that's the last topic that we are going to be talking about today. Before we move on to this IUPAC nomenclature, let me just introduce groups. Groups are chemical hydrocarbons, groups or clusters of atoms that are going to be hanging off an organic compound. Okay? If you look at this black backbone right here, okay, this could be a very long organic chemical. Okay? And if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay, there are 12 carbons in the backbone right here. Okay? And it could be distorted like that, and it could be hidden so that it's not obvious that you have 12. But you have to count the longest continuous chain. And if you find the longest continuous chain, it's got 12. Okay? These things, these purple, I'll remove the purple, but these blue atoms that are attached, they're also supposed to be carbons. Okay, I just give them a different color because they are a group that are hanging off the longest chain. And the rule for organic chemistry is you first need to find the longest continuous chain, and then you name the groups hanging off these. Now, what are the groups? Well, one carbon has a prefix what? Meth. So this is called a methyl, YL. So when we have a group, we give it a YL ending. So when we have a group, groups have the YL suffix. So methyl. Okay, YL. When we have 2 carbons, like this, what is that? Ethyl, exactly. See, it's easy. You guys will be great organic chemists. When we have 3, we have what? Propyl, exactly. And when we have 4, we have butyl. Okay? That's it. That's all you need to know as far as these. Ethyl, methyl, propyl, and butyl. These are the groups. Now, the thing about propyl, I need to elaborate on propyl, is that I could attach it to the main chain, either through the middle carbon, or to the end of a carbon. And they're different. Okay, they're different. So I have to give these special names. This guy, when it's a chain like that, is called N-propyl. When it's a group that hangs off at the end, either this way or this way, it's called N-propyl. When it's connected to the middle, it's called isopropyl. Okay, again, these things are on your cover sheet. You just have to recognize what they look like. The butyls are sort of different. There's 3 ways of doing it. I can do it through the end, in which case it's N-butyl. I can do it through the second carbon, butyl, exactly. Or I can arrange it so that it looks like this. See how I arrange these guys so that it looks like it has a Y in the structure, like that? Well, whenever you see a Y motif, it's an iso group. So this is isobutyl. 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 It's got a Y shape. Just like you had isopropyl, it's got a Y shape. Isobutyl's got a Y shape. And finally, third butyl looks like this. The connection is to the middle carbon, so it looks like a T. Third. Okay? It's like a third butyl. Because it's a tertiary carbon, third. So, no, not third. Okay? Once you understand that, then we can look at the rules. Okay? These are the rules. Okay? The rules are pretty simple once we get going. The first part of the rules is we count the longest continuous chain. We look for the longest continuous chain. Now the longest continuous chain can be very deceptive. Because like I said, it could be contorted like this, and it's not obvious what the longest continuous chain is. I can give you a structure like this. Okay, I can give you a structure like this. Okay, and I can ask you, how many carbons in this guy? And tell me the longest continuous chain. And the longest continuous chain is just a string of carbons. That is the longest. Okay, someone said 8. So let's count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Right, 8. Then I would circle them. Because I don't want to count these again.
So there's another one here, 8.
1, 2, 3, 4, 5, 6, 7, 8.
Does it matter?
No, there's maybe 2.
Oh.
Okay, make it hard for you guys. Okay, so we use that as our backbone. And you have to be persistent in trying to find that longest continuous chain. Because sometimes it's not obvious. Sometimes it's wrapped around itself. So it's just trial and error. So, 8. What's the prefix for 8? Okay. Is there single bonds throughout the backbone?
Yeah.
So we call it an octane. It's not an octane per se, because there's more carbon here, but when we name it, it's got a root name, octane. Okay? Then we circle these guys, because these are groups hanging off. Okay? How many carbons on that? So what is it? Pro? You see that Y? So it's isopropyl. So that group right there is isopropyl. How about this? How many carbons on that? So it's methyl. Okay, good. Now, we've got the parts. Let's just figure out the assignment. You see how this is 3 carbons from the end? And this is 4 carbons from the end? 1, 2, 3, 4. 1, 2, 3. Because this is the shortest path to a group, we call this carbon 1. Okay? The side, the end of the chain that has the closest group is assigned carbon 1. I could assign this 1 or this 1, but since this methyl group is closest to the end, that's assigned 1. So, if this is carbon 1, which part of the chain is the methyl group attached? What carbon number?
3.
So we put a 3 in front of that. Telling you that along the chain, it's attached to carbon 3. How about that? What number is that?
5.
So let's put it together. M before P. So we put 3 methyl. Okay. 5 isopropyl. Octane. That's an H. Yes, it's long, but there is an organization to this. Okay? If I had that name right there, I can make the structure like this. Okay? Start with the root, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons along the longest continuous chain. The number 3 position, 1, 2, 3, I've got a methyl. The number 5 position, 4, 5, I've got an isopropyl. That beast that I wrote previously, this one. Just turn and twist it differently. The name gives you the structure. You use the structure to get the name. The organization is find the longest continuous chain, find the groups, look for the position, and then piece it together. Okay? If there are two groups, suppose I have this right here. You see how I have two methyl groups in the number 3 position? If I added that to the structure, then I would put 3, 3, because there are two methyl groups on that. And then instead of just methyl, I would put dimethyl. The di meaning that there are two methyl groups. So it's 3, 3, dimethyl 5-propyl-octane. Okay. Quick example, quick review. Look at this guy. Longest continuous chain is how many? 5. Which is carbon 1? This or this? The right or the left?
Right.
Right. This is carbon 1, and we have a methyl at the 2 position and the 3 position. So it would be what? 2, 3, dimethyl pentane. Right? 2, 3, dimethyl pentane. Once you understand the rules, organic chemistry nomenclature is not that difficult, at least at this part. Yes?
Why did you start at the right?
Because, you see, this is the longest continuous chain, or I could pick this, right here. That's the longest continuous chain. And that longest continuous chain, I'm just going to circle it, has 5 carbons. So that tells me it's a pentane. It's got single bonds only. Now, you see these groups right here? The closest end would be this carbon. So that's carbon number 1. And that makes this carbon number 2 and this carbon number 3. So the methyls are attached to the 2 and 3 position, and I need to indicate that. Okay? We're not going to talk about alkanes. You guys don't have to worry about that. But make sure you understand how to name these things. Alkanes, there's a bunch of examples. You're not going to worry about alkanes, the naming of that. You guys will learn that in 130. But now you at least understand. Next time you see your drug formula, okay, the one that the pharmacists give you, and you start seeing structures like this, okay, you will understand exactly what these mean. These lines mean, they mean carbon. Hydrogens are implied. These are functional groups. Okay? So, yes.
If there was a methyl on, what is that, 4, and then say a propyl on 3, are you still going to name 2, 4, dimethyl, and then name 3?
If this was a propyl right here,
Yeah. And
then again, you
are
would
you still
want,
going to say dimethane? Or dimethyl?
you would say dimethyl here,
For
okay,
2,
and then you would say 3 propyl. But you need to, you got to be careful. If you have a structure like this, let me erase this, and let me do
Do you know
one.
what I'm saying? Or?
Are you doing 3
I'm
carbons?
just asking if you still, if there's, and then the one on 2, are you still going to call it dimethyl, and then you just put 2 and 4?
Yeah,
Okay.
you still do that.
That's the one.
But going back to this, the longest continuous chain goes from 5 to 1, 2, 3, 4, 5, 6. Okay?
Oh, okay, so
Because, yeah, it messes things up. We look for the longest continuous chain. Okay?